It's my pleasure to introduce President Shirley A. Jackson of RPI. Dr. Jackson is the 18th president of Rensselaer Polytechnic Institute, the oldest technological research university in the United States. Dr. Jackson holds a degree, SB degree in physics and a PhD in theoretical elementary particle physics from MIT, as well as 52 honorary degrees. She has been described by Time magazine as the ultimate role model for women in science. Since 1999, she has led an extraordinary transformation of RPI under a very ambitious strategic plan known as the Rensselaer Plan, now updated as the Rensselaer Plan 2024. It focuses on RPI as a top-tier technological research university with a global reach and a global impact. Her tenure has been marked by a $1.4 billion capital campaign, the hiring over 300 new faculty, a tripling of research awards, and a tripling of applications to the freshman class, and so on and so forth. And it's been a particular honor for us to develop an affiliation with RPI over the last several years, where the work at Mount Sinai and the work at RPI synergizes to lead to research that we hope will change our ability to diagnose and treat human disease. In 2009, President Barack Obama appointed Dr. Jackson to the President's Council of Advisors on Science and Technology. She also serves on the White House Advanced Manufacturing Partnership Steering Committee 2.0, the U.S. Secretary of Energy Advisory Board, and the U.S. Secretary of State's International Security Advisory Board, all indications of her global impact. Dr. Jackson has received many, many awards, too many to name now, given our time constraints. It's an honor to welcome her to the conference and hear her thoughts on engineering and medicine and the potential for that interaction. Dr. Jackson.
Well, good morning, and thank you, Dr. Charney, and I first want to thank all of my colleagues who are here from Rensselaer, because they're the ones who actually pioneer what I get to talk about. And what I want to talk about today is engineering and medicine, a little bit broader than that. Now, as you know, the history of medicine is about expanding powers of observation, enhancing insight, and understanding the basis of disease states, and from them improving, of course, therapeutic interventions to mitigate or eliminate disease and restore health. Now, these objectives emanate from the first understanding of human anatomy and of systems, such as the circulatory system, statistical methods of looking at infectious diseases and the birth of epidemiology, germ theory, and the rise of public health measures, which are credited with adding 25 years to the average life expectancy of the United States in the 20th century. The discovery of X-rays and then other means of seeing inside the body without opening it up, the insights of genomics, which only now are beginning to be more fully tapped clinically, and the as yet uncovered secrets contained in a flood of healthcare data, including that emanating now from our cell phones. I'm talking from that, which can take an electrocardiogram or help to monitor blood glucose. Now, as the SINAInnovations conference has more than proven, medicine now encompasses a multiplying array of disciplines, including nanotechnology, web science, high-performance computing, and advanced modeling, and the entire range of engineering disciplines. The insights of these fields are offering new lenses through which to understand and to treat diseases and injuries. The goal of seeing each patient as an individual and understanding that patient from the molecular level to the level of consciousness and the patient's own experience of health and illness now is within reach. But so also is a new degree of foresight and ability not just to manage and cure diseases, but to enhance the prediction and prevention of them. Now, the possibilities are inspiring, but they will be realized fully only if we can enable collaborations on a grand scale. Consider, for example, the problem of severe spinal cord injury. You may well have heard of the recently reported case of a 38-year-old man who was paralyzed from the chest down after an unfortunate knife attack that nearly transected his spinal cord, but then walking again within a year and a half of receiving a new treatment. That treatment involved bridging the gap in his spinal cord with healthy nerve tissue from the man's ankle and injecting at the site of the injury ensheathing cells from one of the man's olfactory bulbs. The olfactory system, as you know, is one part of the nervous system known to regenerate. The man's returning sensation and muscle control is the result of a promising collaboration led by neurosurgeon Dr. Paweł Tabakov of Wrocław University Hospital in Poland and Professor Jeffrey Reisman at the University College London Institute of Neurology. And it came about after Dr. Tabakov learned of Dr. Reisman's animal studies with olfactory ensheathing cells. Now, a few years earlier, there was an equally striking case of regeneration and another instance of a clinician alert to emergent research. This was the case of a young Marine who lost nearly 70% of his right thigh muscle to a bomb in Iraq. Amputation of the leg was recommended to ease his pain, but the Marine refused. Now, one of his doctors, Dr. Stephen Wolf, then chief clinical researcher for the United States Army Institute of Surgical Research, was familiar with the pioneering research of Dr. Stephen Badylak of the McGowan Institute for Regenerative Medicine at the University of Pittsburgh, work on the extracellular matrix. Now, as you know, this is a fibrous scaffolding that not only provides structural support for the cells of the body, but also regulates cell survival, development, proliferation, function, and migration. This is not the extracellular matrix. But it does include important signaling proteins and draws stem cells to regenerate tissues in all of their differentiated complexity. Now, Dr. Wolf inserted a bit of extracellular matrix derived from a pig into the Marine's thigh, and the muscle regrew to the point that his injured leg became just as strong as the uninjured leg. Of course, a few cases do not allow us to draw completely meaningful conclusions, but clearly, we have come a long way in a few decades. In terms of injuries to the central nervous system, we are well beyond the now obsolete view that neurons can never regenerate, to a number of promising means of encouraging axon regrowth using novel biomaterials such as electrospun fibers, which create a topography to guide growth through scar tissues, electrical stimulation, cell-mediated therapies, including the use of stem cells, the controlled release of drugs, particularly now with advances in nanotechnology, soluble neurotrophic factors released by the supporting cells in healthy nerve tissue. Now, each of these approaches is promising on its own, but studies now being conducted by our own biomedical engineers, Dr. Deanna Thompson and Dr. Ryan Gilbert at the Rensselaer Center for Biotechnology and Interdisciplinary Studies, suggest that there are synergies here and that employing these approaches in combination may prove to be even more powerful for tissue regeneration. Now, at Rensselaer, we are able not merely to look at these factors in isolation, but to take an integrative approach. Biomedical engineers, neuroscientists, electrical and chemical engineers, chemists, biologists, including experts in stem cell research, material scientists, and computational and data scientists work together on problems such as this, on the problems of nerve regrowth, tissue engineering, and regenerative medicine of all kinds. A collaborative effort we hope soon will include the physicians and surgeons here at Mount Sinai. Now, at Rensselaer, we believe that enabling such interdisciplinary efforts is one of the most important roles of a technological research university. These research efforts represent our vision of the new Polytechnic. It is a vision we have articulated as we move to the 200th anniversary of Rensselaer Polytechnic Institute in 2024. And the vision is one of the technological research university as a great crossroads for collaboration among brilliant and motivated people across a multiplicity of disciplines, sectors, and regions, using the most advanced technologies to collaborate and to make advances to answer great global challenges, of course, including the mitigation of disease and improvement of human health. Now, one of the most important aspects of the new Polytechnic is the affiliation, begun 18 months ago, of Rensselaer, a world-class technological research university without a medical school, and the Icahn School of Medicine at Mount Sinai, a world-class medical school without a technological research university. Mount Sinai and Rensselaer will do together what neither one could do alone. To realize the full promise of regenerative medicine, to design new classes of therapeutics based on an understanding of disease that begins at the molecular level, to develop more advanced medical devices, to find better treatments and new avenues for discovery within the enormous and noisy data sets generated by 2.6 million outpatient visits, 500,000 emergency department visits, and 170,000 inpatient admissions each year in the Mount Sinai health system. And, of course, to educate the next generation of both physicians and researchers for deep knowledge, of course, in their chosen fields, but with a broad awareness of the tools and insights offered by other disciplines. Now, our affiliation with the Icahn School of Medicine here at Mount Sinai has in fact been inspired by other successful models of cross-institutional collaboration, such as the Broad Institute of MIT and Harvard, which is, of course, helping to establish and exploit the molecular basis of many diseases. But it is also a fulfillment for us at Rensselaer of a vision that predates, in fact, the completion of the Human Genome Project. Now, as I was being inaugurated as the 18th president of Rensselaer in 1999, we considered the core strengths that Rensselaer could build upon in its research endeavors, and we asked ourselves this question: are there areas that are so vital to humankind that we must create a presence in them, even if we don't already have one, in order to stand in the community of world-class universities and to make a difference? Now, an area in which Rensselaer was relatively unknown, but one that held great promise for humanity that we were compelled to address, was biotechnology. So we focused on 4 areas of promise that built on our strengths at the nexus of the life sciences with engineering, the physical, and computational sciences. And they were biocatalysis and metabolic engineering, computational biology and bioinformatics, tissue engineering and regenerative medicine, and integrative systems biology. Now, with these points of focus, we assembled constellations of star faculty and their research groups, critical masses of exceptional engineers and scientists in key areas of expertise. And we created core facilities to support their work by investing over $150 million to build, equip, and staff our Center for Biotechnology and Interdisciplinary Studies, one of the world's most advanced centers for biotechnology research. We call it CBIS for short. Now, notably, we designed CBIS without departmental offices and with unusually open and flexible laboratory space that allowed for unexpected and fluid collaborations across the disciplines. Now, CBIS today has 60% engineers and 40% scientists in the center doing research. And in the 10 years since it opened in 2004, resident faculty and their students have published more than 2,000 peer-reviewed papers in subject areas that range from protein synthesis and manufacturing to regenerative medicine, biomaterials, bioinformatics, the extracellular matrix, protein folding, and much more. This research has been cited in the scientific literature nearly 30,000 times. Now, this rests on a core of about 30 faculty, their research groups, but their collaborations across the campus with other research groups. But more importantly, the research that they do in the center helps to save lives. Now, allow me to offer an example. In January of 2008, the members of the nephrology unit at St. Louis Children's Hospital became alarmed when some of their pediatric patients suffered severe allergic reactions after being given the blood thinner heparin to prevent clots during dialysis. Now, some of these children experienced dangerously low blood pressure. The hospital notified the authorities, who tracked the heparin to a particular pharmaceutical company that shall remain nameless. But the authorities, in the form of the U.S. Food and Drug Administration, the FDA, contacted one of the first of the star faculty members we recruited in biotechnology, Dr. Robert Linhart, who is the Ann and John H. Broadbent Jr., 59, Senior Constellation Professor of Biocatalysis and Metabolic Engineering. Now, Dr. Linhart was able to assist the FDA in finding the source of the contamination, which was a counterfeit drug that mimics heparin in the laboratory, but not in the human body. And it was added in China to pump up the volume of the product. This deliberate adulteration killed 81 people in the United States alone. Now, the problem with the pharmaceutical heparin that is used is that it currently is derived, in fact, from pig intestines. And since this is the most widely prescribed anticoagulant drug, it requires the slaughter of approximately 700 million hogs worldwide annually. And much of the global supply of heparin stems from underregulated farms and workshops in rural China. But interestingly enough, mixing the food and drug supply chains in this way evokes other concerns beyond the possibility of deliberate contamination. And that is a contamination that can just occur with deadly viruses or prions also then becomes a possibility. Now, at the time of the heparin crisis, Dr. Linhart and his team already were working on bioengineering more safe synthetic forms of heparin. Although producing this complex carbohydrate is an involved process, and it required collaboration among a carbohydrate chemist, a biochemical engineer, a medicinal chemist, a pharmacologist, as well as clinicians, industry partners, and graduate students in many disciplines. Professor Linhart and his team succeeded in devising scalable, cost-effective approaches for producing heparin, and heparin of different molecular weights. So bioengineered heparin now is moving toward commercialization, and we fully intend toward clinical trials, again, hopefully with our partners here. Now, there are many other promising biotechnologies emerging from our laboratories that represent potential revolutions in healthcare, and I will cite just a few. An interdisciplinary team of biochemical engineers and material scientists led by our Vice President for Research, Jonathan Dordick, and John is here. I have very high-priced help here this morning. John is the Howard P. Eiserman Professor of Chemical and Biological Engineering, while being our Vice President for Research. And his colleague, Dr. Ravi Khanna, the P.K. Lashmet Professor and head of the Department of Chemical and Biological Engineering, have devised new strategies for addressing one of the most worrisome challenges facing mankind, the rise of antibiotic-resistant bacteria. But now, by marrying stable nanotubes to specific lytic enzymes that break open the walls of a particular species of pathogen, they have developed long-lasting paints, coatings, and sprays that can wipe out deadly bacteria such as MRSA and Listeria. Now, since the bacterium being targeted in any given case uses the very same lytic enzyme in that bacterium's own process of cell division for reproduction, it cannot become resistant to it. Rensselaer also is generating truly exciting advances in medical imaging. Dr. Ji Wong, the Clark and Crossan Professor in our Department of Biomedical Engineering, is now developing what he calls omni-tomography that includes multiple imaging modalities, including simultaneous CT MRI. CT scans, as you know, offer a map of the morphology of tissues at fine resolution and high speed. MRI, on the other hand, captures functional, flow-related, and tissue-specific signals with excellent contrast. With a simultaneous CT MRI scanner and the ability to combine those algorithmically, we can see both the intrinsic complexity and the dynamic character of real biological processes with important applications in the diagnosis and treatment of cardiovascular disease, cancer, and many other diseases. Professor Asad Oberai of our Department of Mechanical Aerospace and Nuclear Engineering is devising a way to diagnose breast cancer without a biopsy, using an ultrasound movie taken as the tissue is compressed slightly during an exam. It certainly helped people like me. Now, employing massive computational power, Professor Oberai's algorithms actually analyze the varying mechanical properties of the tissue as it moves to identify tumors, to locate them extremely precisely, and to infer whether they are malignant. And the correct positives that he gets is a very high percentage. Now, Dr. Deepak Vashith, who is here today, who is in fact director of our Center for Biotechnology and Interdisciplinary Studies, has taken a material science approach to the bone loss caused by aging that is yielding remarkable new insights. Now, Deepak used to head our biomedical engineering department. And what he has done is recently discovered that a compound called PTB can dissolve the sugary impurities that cause bones to become brittle and to stop regenerating with age. This discovery holds tremendous promise for therapeutics for osteoporosis. And we expect many more such breakthroughs to arise out of joint research with the Icahn School of Medicine at Mount Sinai. Now, it is worth noting that most of the investigations and discoveries that I've mentioned either require sophisticated digital tools or are contributing to an explosion of medical data begging for intelligent interpretation, or both. And as we know, the genomics revolution alone is generating a staggering amount of data. Now, 10 years ago, Rensselaer invested in the Center for Biotechnology and Interdisciplinary Studies to be a leader in biotechnology and this nexus of medicine, the life sciences, engineering, computational, and physical sciences. And now we are investing in the Rensselaer Institute for Data Exploration and Applications, or what we simply call the Rensselaer Idea, for the same reason. The Rensselaer Idea brings together our strengths in web science, high-performance computing, data science and predictive analytics, and immersive technologies, and links them to applications, again, at the interface of engineering and the physical, life, and social sciences in order to expedite scientific discovery and innovation. Now, the Rensselaer Idea is making the highest possible use of the remarkable computational ecosystem that we have assembled at Rensselaer, which includes Amos, the most powerful supercomputer at an American private university as a petascale machine. It also includes Watson, the IBM cognitive computing technology, whose ability to absorb tremendous amounts of natural language information, including articles in medical and scientific journals, and its powerful inference engines, allow it to serve as a data and discovery advisor in medicine as in other fields. And let me just add parenthetically that it was actually Rensselaer people who led the development of Watson at IBM. And Watson is also, in addition to being a tool, is kind of going to school at Rensselaer because we're expanding its capabilities into realms that have to do with inputs in forms other than text, audio, video, haptic. But our computational ecosystem also includes, interestingly enough, our Experimental Media and Performing Arts Center, or IMPACT, which is a world-class center for the performing arts, as well as a state-of-the-art platform for research into data exploration and visualization, haptics, acoustics, and immersive technologies of all kinds. Now, most significantly, our computational ecosystem includes world-class computer scientists who are reshaping the way all of us address great challenges. Scientists such as Professor Deborah McGinnis, who is our senior constellation professor in our Tetherless World constellation, who, as you know, led the previous and moderated the previous discussion and presentations on transformative technologies. She herself is a pioneer in the technologies that enable the semantic web, which promotes common data formats on the World Wide Web, allowing computers to find, bring together, and search structured and unstructured data from many sources to answer difficult questions in medicine and in many other fields. Now, the Rensselaer Idea and the opportunity for data-driven discoveries and innovations in healthcare not only inspired our affiliation with Mount Sinai, they also inspired a new partnership with Optum Labs, a collaborative research center founded by the Mayo Clinic and the healthcare management and technology company, Optum. Now, Optum Labs offers us de-identified claims data from 150 million patients and the scope to consider even uncommon phenomena and rare diseases. Now, using data from these healthcare sources, our folks at the Rensselaer Idea are not merely potentiating groundbreaking research, they are helping the medical system to overcome the economic and regulatory roadblocks that keep us from applying discoveries and innovations clinically. Let me explain. Now, we all are aware of the limitations of a one-size-fits-all approach to therapeutics, that pharmaceuticals are not effective in every patient, and indeed may be toxic to one patient with one genotype while being harmless in another. Now, the ideal of medicines tailored to each patient for every condition will not be realized quickly, given that the FDA approval process for small molecule drugs takes on average 14 years and costs over $2 billion per successful drug. Now, innumerable compounds are in fact screened every year, and fewer than 30 are improved. Now, one of the things that PCAST focused on while I was a member was, how do we begin to help the FDA change and streamline its regulatory process, given all of the advances, the kinds of things you've heard here and the things that I'm talking about. But to realize the promise of personalized medicine more quickly, we need information. Big data, as well as tools to help us analyze and understand that data, can accelerate dramatically our ability to get new treatments to patients at much lower costs, as well as to improve the effectiveness of existing therapeutics by identifying who should receive what treatment. For example, for one of our first 8 joint research projects with Mount Sinai, Professor McGinnis is developing semantic tools for drug repurposing. She is using the results in the published literature to find possible causal relations that suggest which drugs, already proven safe, may be applicable to diseases other than the ones for which they originally were developed, and which new drug cocktails may be effective. Now, the next step is to marry this work with patient data and clinical data overall. But we also hope down the road to inspire investigators at CBIS and Mount Sinai to find a biological explanation for any of these correspondences. And this may well involve, and most likely will involve, using cognitive computing to suggest hypotheses for the researchers to explore. And so the computer scientists and others at the Rensselaer IDEA also are engaged in a data-driven project with a local hospital to explore which patients are likely to develop severe forms of ailments, developing a predictive model to allow earlier intervention and to lower readmission rates for emergency rooms. But they also are working with Dr. Kusum Matthews, again of the Icahn School of Medicine, on intensive care unit triage decision-making with the goal of developing a decision support tool. Now, at Rensselaer, we also are developing tools that may be particularly relevant to a collaborative understanding of disease, as well as a collaborative understanding of particular patients. Now, we have a partner, IBM, and we're combining cognitive computing with high-performance computation and our multisensory environments, such as what we call the Collaborative Research Augmented Immersive Virtual Environment Laboratory, or CRAVE, and impact in a new situations room project. Now, we envision situations rooms that are conjoined physical and virtual environments that automatically respond to their occupants and that engage multiple users simultaneously on different aspects of a problem. Situations rooms could function as multimodal diagnostic theaters that bring together imaging, medical test results, warehouse data from many patients, both structured and unstructured, the scientific literature, and patient data down to the level of the genome so that doctors can make better decisions. Now, we also are focused on educating and how we can help in the education of the next generation of data literate doctors, scientists, and engineers in every field. And we are in the process of ourselves incorporating data literacy throughout the curriculum at Rensselaer for our undergrads. And our PhD in multidisciplinary science now has a track that specifically marries data science to other scientific pursuits. Ultimately, and I know I'm being bold here, if physicians are going to actually deploy new therapies that arise out of research, the education of physicians needs to change in order to encompass not just data science, but a greater understanding of the physical sciences and engineering. To make the most of the remarkable era of discovery and innovation before us, we believe that physicians can partner with non-clinicians to answer medical questions, to use new technologies and tools, and to broaden their own portfolio. Those of us who lead institutions devoted to discovery, innovation, and education have to support and enable better connections among the laboratory, the physician's office, and major medical centers. Now, one of the great strengths of engineering is its discipline in observing, considering, and designing linkages between scales. Now, an airplane, for example, is engineered from materials at the nanoscale, goes to components and devices, to very complicated systems, all of which work together to result in a successful and safe aircraft. Now, airplanes are complex, but not nearly as complex as the human body. And so if we can bring together engineers and researchers in the life, physical, and computational sciences with physicians of all kinds, we will have the opportunity to see, and importantly, to understand health and disease from the nanoscale on up, from the level of the molecule to the cell, to the tissue, to the organ, to the patients in all of their remarkable complexity. The connections we make among people and among ideas will allow all of us to change the world and transform medicine, which is the root of doing that. Thank you very much.